Now that we know how to get from the Riemann sum to the definite integral, let's explore the definite integral a little bit more. We see it right here, and it's got different parts. For starters, we've got the actual integral symbol right there, which is, as we know now, an elongated S, all right, for the word sum. Okay. The A, that's known as our lower or left bound, but we tend to call it the lower bound. And B, that's our upper bound of our region. Right. Both A and B are in terms of x for starters. Okay. The f of x right here, that's known as the integrand. That's the item in which we're trying to find the area underneath. And then the dx, that's known as our differential. Right. That's the base of each of our rectangles. The integrand ends up being the height of each of our rectangles. And we know that this integral right here is the same thing as the limit of the sum as k goes from 1 to n of f of a plus k delta x times delta x. This is the Riemann sum. Okay, what you see right here is the Riemann sum with an infinite number of subintervals. That's what the definite integral is equal to. Okay, we change the Greek sigma into the Roman s. All right, and again, this up here is read the integral from a to b of f of x dx. That's how you would say this. Okay. Keep in mind two things. One, this is just a number. This just represents the area of the region between the function f of x and the x-axis. Okay, the integral is just a number. Also, the variable of integration doesn't just have to be x. We can have u's, we can have t's. The function doesn't have to be f. It could be g. It could be, this could say v of t. All right, and now we're finding the integral of the velocity function. Okay, the variables are not just limited to f and x. But now that we have this definite integral, we have some properties as well. And it's good to know the properties of the definite integral because, in general, they allow us to do so much more with this idea that's coming up known as the fundamental theorem of calculus. Right. With these properties, you can expect a question or two on the exam. The first one is known as our sum difference property, and it basically says that if you're taking the integral from a to b of two or more terms that are separated by a plus or minus, then you are allowed to break it up into two or more integrals. Okay. This is kind of similar to our sum difference rule for differentiation, which is that if you have two items and you're trying to derive them, they're connected by a plus or minus, you just derive them one at a time. The same thing can be said for our integrals right here. The integral from a to b of f of x plus g of x dx is equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. All right, you can split it up. The second property is what's known as the zero property, which basically says that if the bounds don't change, if the lower bound and the upper bound are one and the same, well then here's the situation. All right, we've got our function. Here's a. All right, there's our function right there. We're going to start calculating our area at a, and we're going to finish calculating our area at a. All right, we have a one-dimensional region right here. There's not two dimensions. There's nothing for us to grab, so the area is going to be 0. Our third property is also similar to what we see from the derivative. All right, our constant multiple or coefficient property basically just says that if you have a coefficient, that coefficient can move out front of the integral symbol. Okay, it can now be placed out here, and you just have to integrate the function itself. So coefficients can kind of move right through to the outside of the integral. This is going to come into play big time when we talk about the fundamental theorem of calculus. Next up, we have our order of integration, which basically says that we are used to seeing the integral from a to b of a function. So if it's b to a, in other words, if the larger value is initially located in the lower bound, all right, then things are backwards, because when we're integrating, we're going from left to right. This is saying go from right to left because b is to the right of a. We're used to integrating from left to right, so we can move the bounds back to where they were. The cost is that we have to negate it because, in essence, we're going backwards. So if you change the order of the bounds, you just negate the integral. Because instead of going from a to b, we're now going from b to a. We're going backwards, hence the reason why we have our negative symbol. All right, so again, for example, if we have the integral from 0 to 3 of f of x dx, that is the same thing as the opposite of the integral, excuse me, that should be negative 3 right there. The opposite of the integral from negative 3 to 0 of f of x dx. All right, we can swap the bounds, but we negate the integral. The additive property is a pretty cool one. It basically says that we've got a and b again, and we have c that's somewhere in between. Right? So here's a, here's b, and c can be somewhere in between. Right? So if we want the integral from a all the way to b, let me make our function here. Right? There's f of x. Right? If we want this whole region, well, it's going to be equal to the sum of the two parts. The first part is what's before c, and the second part is what's after c. And if we add the first part to the second part, then we get the whole thing. That's known as the additive property. And finally, we have the domination property, which says that if f is larger than g, greater than or equal to g, on the entire interval, then the integral from from a to b of f of x dx will be greater than or equal to the integral from a to b of g of x. Right? So what we're talking about here is we have a function and we have f. All right, there's f, and then we have g. Right, we'll have g go up and meet it quickly and then back down. All right, and we are interested from a to b. Right, on this interval right here, the f function is always larger than or equal to the g function. So the f function, if we were to find this value, that blue value, or that blue region is guaranteed to have a larger area than the red region. Okay, there's no way it can work otherwise. Okay. The reverse of this, the converse of this, is not necessarily true, though. All right, so basically, if we're talking like, let's say that if the integral from a to b of f is larger than the integral from a to b of g, all right, so let's do this again. All right, so here's f, and here's g down here. All right, we're going from a to b. Okay, so if the integral from a to b of f is larger than g, then that does not mean that f has to be bigger, because we could have a situation like this. Let me switch over to blue. All right, where we drop down a couple times and then back up. All right, so if we look at the blue region, which would represent f, okay, that is larger than the red region, which represents g, the integral from g. So while the domination property is true, the converse of that is not true. Okay. Same thing back up top here, sum difference property. It works for adding and subtracting. It does not work for multiplying and dividing. It's called the sum difference rule for a property for a reason, because we can only add or subtract our breakups, as you'll see on the next couple of examples. If we're multiplying, we have to look at something else.